Hello, welcome to SPMM Revision on Demand. In this podcast, I will discuss the issue of confounders in clinical research and how to deal with them. There may be many reasons why we find associations between two variables in research studies. There may be a genuine causal link between the two variables x and y. While this is what researchers want to conclude from the results, it is also possible that the observed association is a chance finding due to random error. Sometimes, a systematic error in the conduct of the study may also lead to false positive observations. This is known as bias. Finally, the association between x and y may be occurring through a third factor called the confounder. Let us now see the confounder in more detail. A confounder is defined as a factor that is associated with both exposure and outcome and modifies the outcome but not on the causal pathway between the exposure and the outcome. Consider this issue. A study reported a Colombian coffee causes lung cancer. Based on this finding, a fertilizer used in coffee plantations was banned from further use. But could this be a true association? It is well known that people who drink coffee are more likely to smoke when compared to those who do not drink coffee. We also know that smoking is causally associated with lung cancer. Thus, smoking is associated with both exposure, that is coffee, and outcome, that is cancer, and increases the risk of the outcome. In this example, smoking is a confounder. This slide explains the conditions required to be satisfied for a variable to be called a confounder. Let's presume that factor A causes disease B. Let factor X be an established risk factor for B. Factor X has to be associated with factor A, but not caused by factor A. If these conditions are satisfied, then we can call X as a confounder. If confounders create spurious associations between cause and effect, then it is important that the effect of confounders is controlled or reduced when conducting a research study. How can we achieve this? There are several ways to deal with confounders: restriction, matching, minimization, randomization. These four methods are undertaken at the stage of recruitment for a research study. Stratification and adjustment, use of multivariate statistical procedures such as ANCOVA and multiple regression are the methods that are often used at the stage of data analysis after the data collection is completed. The principle behind these methods is the fact that a confounder produces spurious relationships only when it is unequally distributed in the two groups. That is, if a confounder is unequally distributed between cases and controls in a case-control study, between active and placebo arms in a randomized control trial, or between exposed and non-exposed cohorts in a cohort study, only then a confounder can cause trouble. So the methods used during recruitment all aim to reduce the imbalance between the two groups, while the statistical approaches highlighted here aim to account for the imbalance if a satisfactory balance has not been achieved at the stage of recruitment. Let us see these procedures in detail now. Restriction refers to limiting the study participation to individuals who do not carry the potential confounder. For example, you can restrict your recruitment to only non-smokers when comparing coffee drinkers and non-coffee drinkers for the incidence of lung cancer. Obviously, it is impractical to restrict the recruitment on the basis of a number of confounders, else we will not be able to obtain a representative sample. Matching involves selecting controls in a way that the distribution of potential confounders among controls will be similar to those of the cases. For example, for each coffee drinker in the exposed group who smokes, we find a non-coffee drinker who smokes in the non-exposed group. It's important to note that the matching should only be done for the most important confounders and not for all expected differences between cases and controls. By doing such overmatching, one may eliminate the effect of the exposure itself. Randomization is one of the most commonly used techniques. This is often possible when recruiting for clinical trials. Imagine conducting an RCT, randomly allocating subjects from a sampling frame to either drink coffee or to drink milk every day, and following them up for several years to assess the incidence of lung cancers. By randomly allocating the sample, you are increasing the likelihood that a number of potential confounders, including the smoking status, gets equally distributed between the two arms. While randomization promotes equal distribution of confounders, it does not guarantee this. So we need to test the distribution after the recruitment is completed. If randomization has not succeeded, then we must think of tackling the confounders at the stage of statistical analysis. Thus, randomization can take care of both known and unknown confounders, a distinct advantage when compared to other methods that control confounders. Next, let us see the method of minimization. In minimization schemes, next allocation depends on the characteristics of those already allocated in a study. The first few participants are allocated to a treatment at random. For each subsequent participant, we determine which treatment would lead to better balance between the groups. Thus, minimization is a method of elaborate matching after initial randomization. Let us consider an example published by BMJ in 2005. A study is comparing the effect of two types of counseling on weight loss achieved in obese individuals. There are multiple confounders, which, if unequally distributed, may affect the efficacy of the treatment approaches. These include age, gender, ethnicity, and smoking status. At the end of the study, the research team wants to achieve a good balance in gender and in all other confounders between the two treatment groups. This table shows what the research team has achieved at the end of the study. But how did they do this? Let us assume this sample is recruited by using a minimization scheme. The first few subjects, 20 each, are randomly allocated to the two groups. As you can see, we now have a number for the distribution of the confounders for each group. Let us now assume that the 41st person who volunteers is a 53-year-old Asian woman who is a smoker. The current confounder score in behavioral counseling group can be obtained by adding up all numbers that will be altered if this new subject is added to the behavioral group. The score of number of women, age greater than 50, Asian, and smoker will go up. If you add these four numbers, you get a score of 26. Now, do the same for the nutrition group. You get a score of 24. So, adding this new subject to the nutrition group will minimize the overall imbalance between the two groups. So, this person will be allocated to nutritional counseling. In this fashion, all subsequent subjects will be allocated appropriately in a minimization scheme. Finally, we can obtain this nice, well-balanced distribution. Thus, minimization is a useful technique, especially when we do not have a large enough sample to depend entirely on randomization. But we have too many confounders to carry out a matched recruitment. As mentioned earlier, minimization is a compromise between matching and randomization. Next comes the method of stratification. The term strata refers to layer or subgroup. It is a procedure by which subjects in the two groups in a study are classified according to the presence or absence of a confounder. For example, both coffee drinkers and non-drinkers can be classified into smokers and non-smokers. Then, the statistical analysis is conducted in each subgroup or strata to find the degree of association between cause and effect in each subgroup. So, instead of a single 2x2 table, you will be creating a number of 2x2 tables, one for each strata at the end of the study. If the odds ratio obtained from each substrata are similar are not significantly different, we can conclude that the potential confounder has not affected cause-effect relationship in our sample. Finally, a single overall estimate can then be obtained using adjustment methods such as the Mantel-Haenszel procedure. We will see the details of this procedure in the next slide. Mantel-Haenszel is a statistical procedure which helps to pool the various odds ratios after stratification and derive a weighted summary odds ratio value. It is particularly useful when sample size is large, but there are relatively few potential confounders. So, to recap, we have seen a number of methods to control for potential confounders. We will explore multivariate statistics in more detail in a different wordcast. Now, you may want to think of the following questions to help your revision. Thank you for choosing SPMM course for your revision.